So it's composed of two parts. And the first part is composed of two parts. Each part creates a database of useful information. The first part is called Build Awareness Service, which creates database of the build information. And the second part is called the function type database, which creates database of a code information extracted from the original source files. So we will talk today about each part of the system during this talk in details. And a little disclaimer here at the beginning, we are not the developer productivity team. We are the mobile security team. But throughout the years, we built many tools that actually help us during our job, in the security assistant job, on the low-level parts. So that's why we came here, want to share the tools with you. Maybe you find them useful as well. So I hope you will enjoy this presentation. So let's get started with the first part, the Build Awareness Service. So what kind of problem are we facing here? So imagine you need to do a development of a very large software system. So maybe a mobile phone, might be an operating system in your car, or maybe a game engine, etc. Now imagine that what you need to do is to learn how this software is built, what is the structure of this software, which part it consists, etc. So now what is the problem? So let's take a mobile phone as an example. So the complexity of today's smartphone is extremely large. Like for example, when you download all the source code for the Android AOSP open source project from the repository, you end up with around 1 million files, right? And if you focus only on the low-level native part of the operating system, the C and C++ files, you still have to deal with more than 300,000 files. So the complexity is very large, like you have several thousand modules to deal with. And the situation is even more complicated than that, because you can build many distinct products from one source tree, or different variations of one product. So for example, actually only a subset of files is actually used to build a specific configuration. And finally, you have preprocessor definitions and in the C and C++. And inside source code, you have a conditional inclusion of code based on these preprocessor definitions. So actually a different part of one source file can be used in two different build configurations. So how could you know if the code you're looking at is even running, right? Because we want to avoid the worst nightmare of software engineer, that you're looking for some issue and you think you found some problem, you analyze it for 1 or 2 days, right? You create the POC, you just push it onto device, run it, only to find out that the code you were looking at was not even compiled, right? So how can we know if the code we're dealing with is a part of the product? So actually the build system can create the final image, which you can take, you can download, you can flash it, and it even works, right? So actually all this information is located inside the build system. So what kind of information is that? So we have information about which source files are compiled, exactly how they are compiled, dependencies between the build files, or usage of some custom tools, because some tools can actually generate some headers or sources. So what we need to do here is just to trace the build and just grab all the information that we need. So there are two questions. So what do we need to trace, and how can we do this? So the first answer is we need to trace all the files that were opened during the build, the open syscalls, and also all the processes executed during the build, the execv syscalls. And how can we do this? So we tried several approaches. So we tried the LDP load trick, we tried the ptrace. Actually, the ptrace worked for some time until we started doing some builds on a large servers, more than 100 threads, and when it finally broke. So finally, we implemented the tracer inside the kernel as a Linux kernel module. We traces all the syscalls inside the kernel. It saves the information into the Linux kernel tracing infrastructure buffers. So regarding the overhead of this tracer, so of course it depends what the build system does exactly, but on average, during the full Android build, we have overhead around 5% in the build time. So here's the BAS architecture. It's quite simple and straightforward. So we have this build tracer that tracks the build and saves the raw syscall information to the file. It's then post-processed to actually create some intermediate file like a JSON. Of course, you can take this JSON and just put it to the proper database if you like. And we have the applications which just use this to support the developer productivity of the engineers. So two things to mention here. some of the commands executed during the build have a special meaning, like, for example, compilation commands for the C and C++. So these are which interest us, so we analyze them further to actually extract some additional information from them, like preprocessor definitions defined on the command line of each compilation, or some include paths defined at the command line, or files included actually through the command line, etc. So, and another thing to mention here is that we have some functionality to actually compute the file dependencies between files, the build artifacts. So, for example, we can compute and know exactly which files were used to, for example, create some module like a linked kernel executable. So this is the BAS architecture, and let's now, Adrian will tell you about some applications of the BAS, how this can be useful.
Thank you, Bartosz. I would like to present you some practical examples how BAS service can be used to increase development productivity, and especially in the case when working with code and build systems. So let's start with code search improvements. So BAS can improve working with code by narrowing this code base, so both manual inspection and code search utilities may greatly benefit from it. Due to the fact that BAS contains information about every open files during tracing, we can easily get the exact subset of files that were used to create our product or any of this part. As you can see on this example, the full Android AOSP tree consists of more than 1 million files. But after building, we found out that only 166,000 files are actually involved in the build process. This subset is even smaller in case of common kernel tree, where 8,000 out of 98,000 files were used during build. And similar results can be observed in second example, when searching for a specific keyword. The GPO phrase was found around 200 times in build files, which is around 9% of all GPO in full source set, and about 5% in common kernel tree. So we can imagine that such a view of minimal subset of source files, which may be around 10 times smaller, can be really useful when dealing with code search and code analysis tools. So we all know that IDE can improve working with sources, so that code completion, symbol references, support for defines, and even macro expansion. All these features require proper code indexing. Imagine that we want to create a project in our IDE that will consist of only files used to build this VM Linux kernel. And with the help of BAS, we can easily generate minimal subset of dependent files and fit them into project structure. But opening this file, for example, in Eclipse CDT, may result in many indexing errors, like missing files, unknown symbols, and others. Why does it happen? Because in order for indexer to operate properly, it needs exact compilation switches used during the build. Especially, it needs to grab preprocessor definition passed to the compiler through command line. JSON compilation database can help with that problem. It is the file that contains commands with all arguments used during compiling the files. Compilation database file format is supported by most IDEs with C indexing feature and can be easily generated by using BAS. It's worth mentioning that BAS can also generate additional information, like internal compiler definition that can increase indexing precision even more. As a result of adding this compilation information, we get almost perfect indexing statistics, which is in there, and this translates to the better code browsing experience. So, build systems are very complex software. I bet that many of you stumbled on some build problems from time to time. And when a build fails, having a process visualization can help navigating the hierarchy of the build commands and makes it easier to trace back to the exact point where error occurred. By using information about process hierarchy, BAS can be used to build service, for example, as a form of web application that allows user to browse this process tree and can assist in verifying that the right build commands, compiler flags, and other options are applied consistently across all build items. We can also analyze the build flow, and that provides step-by-step view of build sequence, which may lead to resolve some dependency problems. In this example, on top we see a make file, which compiles a single source file and produces the executable, and below we can see or not the process hierarchy that may be produced from this build. Now let's move to another example, which is execution time measurement. So BAS database contains a lot of information about traced process. Among them are process creation time, duration, average CPU utilization, and a list of events with CPU core association. And having such information allows us to create a timeline of CPU utilization of our build process. Next, we can check if there are any suspicious periods in our timeline, like timeframes with very low CPU utilization. Inspecting the time frame will get us information about all processes that have been running in a given period of time, and information about which CPU was used to serve events of this process. So we can spot, for example, some parallelization problems when most of cores are idle, or long-running tasks that blocks our build progression. Analyzing this information can lead to better understanding what happened during build, and it may give us clues about what caused the bottlenecks in our build system. Another example how we can utilize BAS database is a build dependency graph. And thanks to the process hierarchy and open files information, we can generate a file dependency tree of any file. And by file dependencies, we mean the list of files that were used directly or indirectly to create a given file. And implementing such dependency tree, for example, as form of web application, can help us understand the relationship between modules and files. This can aid us in dealing with issues in complex build systems. Like in this example tree, we can see that some tree branches are linked modules, and that consist of other dependent modules and files. So if we, for example, change one CPP, all parent branch nodes are potentially affected and will need to be rebuilt. Thanks to dependency analysis I will show in the next example, we can also implement custom-built scripts where only the necessary tasks are executed during when the source code changes. And this can save time and resources by avoiding unnecessary recompilation or rebuilding. So, another example of using BAS is utilizing process information to generate build-like scripts. So the first thing we have in mind when it comes to the build system is compilation, and the most problematic aspect of compilation is build time. So luckily, incremental builds was invented and can save a lot of time and narrow the compilation to small parts of code that were changed. But in large projects, even though incremental builds are available and we bravely assume that they're working flawlessly, the build system can take a few minutes before actual compilation starts. So generating selective make files or build scripts for desired subset of files, all replaying the build of the files and its dependencies without even running the whole build system. Of course, this is the only case when the build configuration did not change. And such selective build script can greatly shorten development build to test cycles. There are also plenty of tools like Clang Static Analyzer, linters and checkers that can be used with build scripts. and the BAS can generate them easily. We can also generate scripts that can replay any command of our original build. Like in this example, we can extract the list of Java compilations and prepare them for injecting Java-C compiler plugin by using postfix or prefix. By looking at previous examples, some of you may wonder how to get all this information about compilers, files, dependencies, IDE project, and makefiles. So CA repository contains command line tool designed to process trace file into database and query for all sorts of information. So using BAS command line is quite simple concept. We run the client with commands dependent on what we want to get in return, like linked modules, reference file, dependencies, or compilation info. Then we add some additional arguments like filtering, sorting, or limiters, and we get the results. Command line includes a filtering engine that supports logical expression, file and executable types, path matching, and many more. So as you can see in the first example, we use the filter to only get existing files that are placed under the source root directory of our project. This is in fact the easiest way to get the minimal source set described in the first example. Commands can be chained. It means that output from one command can be redirected as an input to another command, and we can see this in second example. First, we use linked modules with a filter for VM, Linux, and KO. And then we pass these results to the dependency command and add some arguments for IDE project generation. And this example is how we can generate IDE projects for kernel and all its modules. And in the last example, we can see a makefile generation of all commands using Java-C binary, like in previous example. But what can be even more useful than command line? A nice web UI. And BAS provides this as well. So BAS web service share the same code base as a client. So thanks to this, both have the same functionality. And as you can see in examples, even URL queries are very similar to console commands. Web service gives us freedom of remote access, which is essential when dealing with large infrastructure. And the web access can also decentralize the location of tools and services which utilize web API. So to summarize, both web service and command line are simple to use yet powerful tools that can be used to query your trace database. But what if this is still not enough? You can take matters to your own hands and use programming API. So both command line and web service are built on top libtrace library, which is part of the CAS project. And this is highly optimized C-based library intended to be used within Python code. It contains database engine and a set of functions for data query, dependency generation, and filtering. Repository contains Python interface files, so your IDE will assist you in code hints and documentation. And usage is simple. With just a few lines of code, we can initialize and load trace database. And after that, we grant access to a variety of functions and objects for querying data about your trace build. So following example gets kernel file path and iterates its file dependencies, looking for a header file related to dependent compiled files. So as a result, we get the map of every header file with a list of compiled files that somehow uses this header file. And this one is end of bus example part, but I would like to conclude this with a little summary. So in our examples, we focused on using BAS in the build system, but it can be used in very generic scenarios. So BAS can be used to trace executable, process trace information into database, and query it for all sorts of information. And this information can be reached in many ways, like command line, web interface, or programming API. And on the final, we believe that based on our security experience, that BAS can open new possibilities that will help you work with your code and the build system. So I will now hand over to Bartosz, who will continue discussion about CAS.
Thank you, Adrian. So let's now focus on the second part of the CAS system called function type database. So this is the part that actually creates the database of the code information extracted from the original source files. Okay, so now we have the perfectly indexed IDE with all the relevant source code. So now we can finally start the software engineering job. So let's imagine that you have a task to actually make a source code review of some module, like for example, some Linux kernel. So what do you need to do? What would you do to actually find software problems in this module? So you probably rely on your experience to try to find some erroneous patterns in the code. So, but we have still this problem, like we have a lot of source code to review, like for example, 4,000 files for the VM Linux linked kernel executable. So what we can do here is to try to apply some automation, like for example, run some dynamic analysis tools like fuzzers or sanitizer, etc. But how to improve the source review process itself, right? So there's this idea. So what if anyone that works with the code and have the willingness and capabilities to do this could write their own tools that operate on the source code in any language they want. So in that case, you would just transfer your own pattern recognition mechanism of the erroneous source code into some more automated form. And this could also work at scale. So in order for this task to be successful, we need to parse the source code somehow, the C and C++ source code. So how can we do this? So maybe we can write some regular expressions, right, to parse it, but probably you can write very simple regular expressions before this task become unmanageable. So maybe we can write our own parser, but actually in order to write the parser, you first have to write the preprocessor, and this is a very difficult task in itself. And even if you succeed with this task, then you have to face the complicated grammar of the C and especially the C++. So actually, the reality is that you cannot write your own parser from scratch. So, but hey, there are a lot of compilers out there working, right? So why don't we just take the parser from there? So actually, there is something that we could use straight away. So we have this Clang frontend for the LLVM. So the beautiful thing about Clang is that just a collection of the libraries that implements the compiler functionality. So maybe in that case, we can just write the parser library and write our own application that will parse the source code and create the parsed representation of the C or C++. So now, what is this parsed representation? So it's a sort of a tree, and it's called abstract syntax tree. So it's just a tree-like representation of the C source or C++ source file. And so it's a tree of nodes, and each node actually implements, it's a C++ class that implements some part of the source code grammar. So as you can see on the example, there is a very simple code and the AST representation of this code. So if this is a tree, so it's easy to walk, easy to traverse, right? So you just need to write the C++ code that uses this parser library and just walks the entire tree and implements the functionality of your specification. So the problem is that every time you want to write an application that performs some, I don't know, some static analysis, you have to write it from scratch and use this parsing, walking about this tree. So how about we write the code once, walk the entire tree, and extract some features from the source code, the predefined features, and just put it into some database like a intermediate format, like a JSON file. So this is exactly what the function type database is about. So we have this Clang-based processor that walks the entire AST for the entire kernel code, for example, or other module, and just extract some predefined features and save it into the JSON file. So what do we extract? We extract information about the functions, information about types, global variables, and also some initializers for function pointers in the global structure types. So here is some example of the simple code, simple function, and there's some excerpt from this JSON representation. So for example, we have information, the function name, there's function name. We have the types of the arguments in this function, and we also have, like here, we have the IDs into the type array of all types defined in this JSON. And we have the all functions called within the body, and we also have the calls like the IDs to the function array in this JSON. We also have information about all these local variables defined in this function, and there are much more, like for example the original body, the pre-processed body, information about some expressions, like for example some dereference expressions of pointers, etc. So one important information to mention here is that we have information about all the types, so we can regenerate the code back from this JSON representation if we need, for example, code that defines some types. So let's now look at some examples how the FTDB actually could be used in practice to actually support the developer productivity of the engineers working with the low-level code. So similarly to the BAS, we have the nice Python API, which allows you to write programs that operate on source code in the Python language. So, for example, you can write a few lines of Python code that actually performs some simple static analysis of the original C code. So, as in this example, what it does, it just checks if any argument of our calling function was passed to the size argument of all the memcopy invocations across the entire kernel code. So, and we want to check that because we want to verify if there's a chance if the data that comes to the size argument was actually can be controlled by the user, because if it does, there are potential for the security vulnerability. So in that case, we just look for invocations and follow the call hierarchy up to verify if this can be controlled. And as you can see, this few lines of code gives us a result, about more than 700 results, such invocations in the entire kernel, Android common kernel code. And another example, very similar, like we have write some few lines of code that actually generates the call graph of a specific function with a given depth. So for example, here the lines 15 to 25 generates the call graph of this DRM IOTL function with a depth of 2, and you can see this graph there. But these were simple examples, but you can also build some more advanced system based on the FTDB. So for example, imagine a system that could actually extract a list of interesting functions from your target and just present it to you in the IDE-like manner. So for example, you could see the original code, you could see the pre-processed code, you could see diffs between the previous revision of or different OS version. You could have some IDE-like features like for example, taint on the arguments or some marking of some interesting functions, etc. So all the things that makes the source code review easier. And this system could apply some heuristics to find some erroneous patterns in the code and just present the extracted functions in a probability of error in mind. So what kind of heuristics that it might be? So it might be a cyclomatic complexity or some memory usage patterns, or for example, usage of some dangerous functions in the call hierarchy, etc. And you could write your own plugins that actually implements extracting the functions according to your target, and you would have available some search engine that you could create some advanced code queries that looks for some erroneous patterns and just present it to you in the source review pane. And another example is that you can create test data that follows a specific structure. So for example, imagine that you need to test some implementation of some protocol, and this protocol has some pointer to the payload, and this payload also has some pointers to some strings. So in that case, you want that if you generate this test data and feed it to your application, you want this test data to follow this structure. So because you want to modify only the values, and you don't want modifying the pointers, because otherwise, if you apply some dynamic analysis tools like fuzzers, you would end up with a lot of crashes, a lot of issues, and most of them would be false positives because they would originate if you change the pointers and you run your application, that would just crash on those invalid pointers. So you want to follow the structure. So the FTDB contains all the information about the layout of the types, layout of the structure. So you can use this to actually generate code in your test application that will initialize this data every time the test is executed to this proper structure. So it's called structure-aware testing. So, and now I want to tell you two more applications that are a very good example of some tools, standalone tools to actually can improve the productivity of the software engineer, but also a very good example how those tools use the FTDB to actually improve their operation. So the first tool is the called Auto of Target, a project. So what is the AOT? So imagine that you want to test a piece of software that is otherwise very difficult to test. So for example, you might have some parser embedded deep down in your WLAN driver, and in order to test it, you need to set up the connection and then send the messages over the air. And so you have natural limitation in the throughput, so your automatic testing would be very slow in that case. And what do you need to do? So, and also what to do in case of crashes, right? It's not easy just to take the WLAN firmware and just run it under the GDB for debugging. So you look for some alternatives. And one of them could be off-target testing. So what is off-target testing? So you just take this parser functionality and just extract it from your full driver code and just compile on your development machine, create the executable, and just feed the messages to this executable, to your parser through this executable. So in that setting, you would have access to all the tools available on your development machine, right? You could use GDB, you could embed coverage information, you could use fuzzers, you could use sanitizers, Valgrind, even symbolic execution is possible in that case. Of course, I assume that the parser doesn't depend on the hardware very much, so it's just a portable C code that shuffles around data between buffers and it doesn't write to the CPU registers directly. So how to create the off-target? So you take the main parser function and just try to compile it. Probably it will fail because there are missing dependencies. So what you do, you just pull more code, like more type definitions, more functions, dependent functions, more global variables, etc., and just try to compile again. And probably need to do many such iterations until your code finally compiles. So as you can see, it's quite a painstaking job actually to do this task. So the AOT project was born to actually automate this process. So you can see there's automatic in the name. So what you can do, what this tool does, it just extract and creates the off-target harnesses from a larger code in an automatic fashion. So if you're interested more in this project, you can see a GitHub repository or read our paper or see our talk from the CLI workshop last year. But the main point here is that the AOT uses the FTDB database exclusively to operate on this data because it has everything that it needs regarding functions, types, and globals. Okay, and another example is the KFlat project. So what is the KFlat project? It's a tool to actually serialize memory variables from C programs. So it does so, but just recursively walking all the dependencies of a given variable and just copies its memory. And it creates a flattened image, so you can just read it back very quickly on your machine. So let's take a look at the example from our protocol example. There's some memory structure. And now if you have some variable inside the C code, like here, that actually this is an entry point to this structure, so you can just feed it to the flattening engine. And what it does, it produces the continuous memory region with all the copied data and all the pointers resolved inside this continuous memory region. So we can take this memory and just save it to the file and just, store it somewhere, right? And then you can restore it back on some different computer at different time, a different continent, for example. So there's some simple function call that just restores the memory very quickly. So how it does this serialization? So what it needs some user-defined recipes to actually create this serialization. So you have to tell it how to do it. So each recipes actually defines a function which is used to actually copy the data of some structure. And inside these recipes, you have to execute some other recipes for all the dependencies. For example, here we have this payload, which is a pointer. So we tell that, okay, so this payload is a protocol data structure, so just execute recipe for this protocol data structure. And this protocol data structure have another recipe for name and description. You can see the name and description are test string, so this recipe just copies the memory of the string until it finds the 0, and all the dependencies are resolved. So how this can be actually used in practice? So imagine a system that some tool, for example, that need to read a lot of or compute a lot of data before it actually starts doing something useful. So a very good example of that would be some build system, for example, like it can take a few minutes before it actually reads all the make files before it gives you some very small incremental build. So in that case, what we can do here is just take the memory image of all the parts make file from this tool and just save it to the file, and next time you execute this build, and assuming the make file didn't change, it can be read back in a matter of milliseconds. And another example is more the kernel side example. We can use this tool to actually extract some debugging information from the kernel, or for example, getting some periodic snapshots of data from the kernel for the tracing purposes. So here's the example of very simple recipes that actually dumps all the task struct information from the running kernel. Task struct actually describes information about the process running in the Linux. And here is an example of some simple user space application which just reads this data and prints some information from it. And now, what's the problem here? Some structures, dependencies for some structures can be really huge. So for example, in the case of the task struct, you can actually reach more than 3,000 different dependent structures if you just follow all of them. So in that case, you would need to write the 3,000 different recipes, right? So it's quite a difficult task to do. And now the FTDB comes in handy because it can be used to actually try to generate all those recipes, because we have, again, information about all the layouts of the structure. So yeah. So to summarize, if you are interested more in the K-flat or just more in the recipe generation, you can see the GitHub page or see our talk from the Open Source Summit this year. But the main point is that we can use the FTDB information to actually try to generate the recipes which are responsible for the proper K-flat operation. So finally, let's summarize what we've been talking about today. So we talk about the BAS system, which creates the database of the build information, which can be used to actually, improve the code search or improve the indexing utilities of your IDE, or can be used to visualize some build information or some dependencies, etc. And also, we have the function time database, which creates the database of some code information extracted from the original source files, and it can be used to generate some off-target harnesses extracted from the larger source code base, or can be used to improve your source review systems, or it can be used to create some structure-aware test data for your testing. So one more thing to mention here is that regarding some language compatibility. So you can imagine the BAS as a tool, which actually it's some operating system level utility. So actually it works. It works with all the build systems, for example, because it traces the syscalls on the operating system level. But as I mentioned, there are some we implemented because we needed them. We implemented some extracting some information for the compilation commands for C++, but you can easily extend it to some other languages like Rust or Java or anything. And another thing is that the FTDB works currently only with the C code, but the implementation with the C++, or at least the C part of the C++, is on its way. So we plan to push it to the open source in the future. So to summarize, the software systems are extremely complex these days, and the CAS can help you navigate through this complexity so it can improve your tools and allows for more automation while you're working with the code, and also it creates the fundament of the for the developer productivity engineering on the low-level system code. So thank you very much for your attention. The feedback is highly appreciated. So we have the CAS is an open source project, so you can access it GitHub repository. So it's just file an issue or just create some PR if you have some nice functionality, or just send us email with any critique that you find appropriate. If you have any question, we can try to answer now, or you can find us at any point during this conference. So yeah, thank you for your attention and see you next time.